Lesson Introduction. Managing user authentication and authorization is only one part of building secure information technology services. The network infrastructure must also be designed to run services with the properties of confidentiality, integrity, and availability. While design might not be a direct responsibility for you at this stage in your career, you should understand the factors that underpin design decisions so that you can assist with analysis and planning. Lesson Objectives. In this lesson, you will do the following. Compare and contrast security implications of different on-premises network architecture models. Apply security principles to secure on-premises network architecture. Select effective controls to secure on-premises network architecture. Ensure secure communications for remote access and tunneling. Exam objectives covered. 3.1 Compare and contrast security implications of different architecture models. 3.2 Given a scenario, apply security principles to secure enterprise infrastructure. While you may not be responsible for network design in your current role, it is important that you understand the vulnerabilities that can arise from weaknesses in network architecture and some of the general principles for ensuring a well-designed network. This will help you to contribute to projects to improve resiliency and to make recommendations for improvements. Architecture and infrastructure concepts. Network architecture means the selection and placement of media, devices, protocols/services, and data assets. Network infrastructure is the media, appliances, and addressing/forwarding protocols that support basic connectivity. Network applications are the services that run on the infrastructure to support business activities, such as processing invoices or sending email. Data assets are the information that is created, stored, and transferred as a result of business activity. Secure network infrastructure and application architecture are put there to support secure business workflows. A workflow is a series of tasks that a business needs to perform, such as accepting customer orders from a web store. Remember that security means the attributes of confidentiality, integrity, and availability. Analyzing the systems involved in provisioning email can illustrate the sorts of architecture decisions that need to be made. Access. The client device must access the network via a physical channel and obtain a logical address. The user must be authenticated and authorized to use the email application. The corollary is that unauthorized users and devices must be denied access. Email mailbox server. The mailbox stores data assets and must only be accessed by authorized clients and, conversely, must be fully available and fault-tolerant to support the genuine user. The email service must run with the minimum number of dependencies over network infrastructure that is resilient to faults. Mail transfer server. This must connect with untrusted internet hosts, so communications between the untrusted network and trusted LAN must be carefully controlled. Any data or software leaving or entering the network must be subject to policy-based controls. This type of business flow will involve systems with different security requirements. Placing the client, the mailbox, and the mail transfer server all within the same segment will introduce many vulnerabilities. Understanding and controlling how data flows between these network segments is a key part of secure and effective network architecture design. Network infrastructure. It is helpful to use a layer model to analyze network infrastructure and services. The Open Systems Interconnection (OSI) model is a widely quoted example of how to define layers of network functions. A network is comprised of nodes and links. At the physical (PHY) layer or layer 1 in the OSI model, links are implemented as twisted pair cables transmitting electrical signals, fiber optic cables carrying infrared light signals, or as wireless devices transmitting radio waves. There are two types of nodes. A host node is one that initiates data transfers. Hosts are usually either servers or clients. An intermediary node forwards traffic around the network. This forwarding occurs at different layers and with different scopes. A network scope of a single site is referred to as a local area network, LAN. Networks that span metropolitan, countrywide, or global scopes are called wide area networks, WANs. Each network node must be identifiable via a unique address. This addressing function also takes place at different layers with different scopes. Forwarding and addressing functions are handled by the following network appliances and protocols. Switches forward frames between nodes in a cabled network. The network adapter in each host is connected to a switch port via a cable. Switches work at layer 2 of the OSI model. Most LANs use networks based on the Ethernet standard. An Ethernet switch makes forwarding decisions based on the hardware or media access control (MAC) address of attached hosts. A MAC address is a 48-bit value written in hexadecimal notation, such as 00155D01CA4A. This addressing works within the local network segment only. This is referred to as a broadcast domain.
Description.
The model includes 7 layers: Layer 1, Physical, Layer 2, Data Link, Layer 3, Network, Layer 4, Transport, and Layer 7, Application. The data link layer includes a switch and an access point. It has MAC address 00-15-5D-0-1-CA-4A and VLAN ID 100. Network layer includes a router and an internet protocol. It has IP address 10.10.192 and subnet 10.10.0/24. Address resolution protocol is between the data link layer and the network layer. The transport layer includes transmission control protocol and user datagram protocol. The application layer includes a server and application protocols such as HTTP, SMTP, SMB, FTP, and DNS. It has a fully qualified domain name, www.515support.com. Domain name system overlaps transport and application layers. Appliances, protocols, and addressing functions within the OSI network layer reference model. Images copyright 123rf.com. Wireless access points provide a bridge between a cabled network and wireless hosts, or stations. Access points work at layer 2 of the OSI model. Wireless devices also use MAC addressing at layer 2. Routers send packets around an internetwork, making forwarding decisions based on Internet Protocol (IP) addresses. Routers work at layer 3 of the OSI model. Each local segment will normally have a router connected to it. The router acts as a default gateway for hosts on the segment to use to send packets to other segments. Transport protocols allow clients to exchange data with application servers. The Transmission Control Protocol (TCP) establishes reliable connections, while the User Datagram Protocol, UDP, allows unreliable, connectionless transfers. Each application protocol is identified by a TCP or UDP port. This functionality is defined at layer 4 of the OSI model. Application protocols support client-server functionality for user-level services, such as web browsing, email, and file transfer. Application protocols work at layer 7 of the OSI model. Domain name system, DNS, servers hostname records and perform name resolution to allow applications and users to address hosts and services using fully qualified domain names, FQDNs, rather than IP addresses. DNS also works at layer 7 of the OSI model, but is an infrastructure service, rather than a user-level service, like web browsing. The OSI model has 3 upper layers. In practical terms, distinguishing the functions of layers 5, 6, and 7 isn't that helpful, so just think of applications working at layer 7. Rate your Switching infrastructure considerations. The basic function of network infrastructure is to forward traffic from one node to another. At each layer, nodes and links are arranged in a topology that best fits the application workflows in terms of performance and security. A topology is a diagram showing how nodes are physically or logically connected by links. An on-premises network is one installed to a single site and operated by a single company. This can also be referred to as an enterprise local area network, LAN. We will focus on this type of network first and review the architecture of cloud and embedded systems networks later. On-premises switching infrastructure starts with the cable layout. Offices and multi-building campus networks are typically installed in a standard way, referred to as structured cabling. Wall ports provide connectivity for each workstation. A patch cable connects the network adapter in the PC or laptop to the wall port. Structured cabling is run from each wall port through wall and ceiling conduits or voids to a patch panel. Another patch cable connects the port on the patch panel port to a switch port.
Description.
The components are as follows. 1. Patch cable connects the computer's network card to wall port. 2. Structured cable runs through wall or ceiling conduit from wall port to patch panel. 3. Structured cable terminates to back of patch panel. 4. Patch cable connects patch panel port to switch port. Physical topology of components in a structured cabling system. This can be described as a star topology. The switch sits at the center with links to hosts radiating out. The switch can establish data links between any two hosts that are attached to it. Also, if a host sends a broadcast to all local nodes, the switch ensures but does not verify that it is received by all the connected hosts. This is referred to as a broadcast domain. The hosts are all part of the same layer 2 local network segment. This basic star topology exhibits a number of issues. Broadcast domains with hundreds of hosts suffer performance penalties. The network segment is also flat in terms of security. Any host can communicate freely with any other host in the same segment. Freely means that no network appliances or policies are preventing communications. Each host may be configured with access rules or host firewalls or other security tools to prevent access, but the view from a network is that hosts in the same segment are all free to attempt to communicate. These drawbacks mean that large networks use a hierarchical design with 2 or 3 forwarding layers. In the hierarchical design, there are a number of blocks served by access switches. Each access block is a star topology for a group or block of network hosts served by an access switch. The access switches are connected by routers. These routers create separate broadcast domains and can control the flow of traffic between blocks. As each block can have different access policies, this topology allows the creation of a zone-based security model.
Description.
The hierarchical structure includes routing or IP addressing, core, access, and switching or MAC addressing. A router or layer 3 switch is connected to a border router or firewall and to the 3 access switches. The first access switch is connected to printers, the second is connected to workstations and VoIP handsets, and the third is connected to the private app and database servers. The border router or firewall is connected to an access switch which is connected to a Wi-Fi access point, which, in turn, is connected to the guest network. Network with a basic hierarchical structure. Access switches implement blocks of hosts with similar security properties, such as printers, workstations, servers, and guest devices. Communications within a block uses MAC addressing and the forwarding function of the access switch. Communications between these blocks must flow through routers in a core layer and uses IP addressing. You will often see the term Layer 3 switch. These are appliances that implement the core network. They perform a combination of routing and switching. There are many types of switches with different roles to play in on-premises and data center network architectures. While client workstations connect to network switches via wall ports and patch panels, servers and core networking appliances are usually installed to a separate, secure area, referred to as an equipment room or server room. Server computers can be connected directly to switch ports using patch cables. Rate your confidence. Routing infrastructure considerations. Layer 3 forwarding, or routing, applies a logical addressing scheme to identify each network. Layer 3 architecture represents the logical segmentation of networks and the creation of networks within networks, or subnetworks, subnets. Each subnet is a separate broadcast domain. At Layer 3, nodes are identified by Internet Protocol, IP. Addresses and links are identified by routes. Internet Protocol. Internet Protocol, IP, provides the addressing mechanism for logical networks and subnets. A 32-bit IP version 4, IPv4, Address is written in dotted decimal notation, with either a network prefix or subnet mask to divide the address into network ID and host ID portions. For example, in the IP address 101.10/24, the /24 prefix indicates that the first 3/4 of the address, 10.1.1.x, is the network ID, while the remainder uniquely identifies a host on that network. This /24 prefix can also be written as a subnet mask in the form 255.255.255.0. In the hierarchical network architecture, each access block can be designated as a separate IP subnet. This system of layer 3 logical addressing makes it easier to write access control rules for what traffic is allowed to flow between blocks or zones.
Description:
A router or layer 3 switch is connected to a border router or firewall via an inline proxy firewall that has a subnet 101.128.0/24. It is also connected to 3 access switches through subnets 10.1.48.0/24, 10.1.32.0/24, and 10.1.16.0/24. The first access switch is connected to printers, the second is connected to workstations and VoIP handsets, and the third is connected to the private app and database servers. The border router or firewall is connected to an access switch through a subnet 192.168.420/24. The access switch is connected to a Wi-Fi access point, which, in turn, is connected to the guest network. Each access block has been allocated a subnet. The guest network is logically separate from the enterprise LAN and uses a completely different IP network. Networks can also use 128-bit IPv6 addressing. IPv6 addresses are written using hex notation in the general format 2001, DB8, ABC 0, def 0:1234. In IPv6, the last 64 bits are fixed as the host's interface ID. The first 64 bits contain network information in a set hierarchy. For example, an ISP's routers can use the first 48 bits to determine where the network is hosted on the global internet. Within that network, the site administrator can use the 16 bits remaining out of 64 to divide the local network into subnets. A packet that is sent via IP has to be forwarded using layer 2 addressing. IPv4 uses the Address Resolution Protocol, ARP, to map a host's IP interface to a MAC address. IPv6 uses the Neighbor Discovery, ND, protocol for the same purpose. Virtual LANs. Mapping the logical IP topology to physical hardware switches is not always straightforward. This problem is addressed by the Virtual LAN (VLAN) feature supported by most switches. All switches connected together on the same on-premises network can be configured with a consistent set of VLAN IDs. A VLAN ID is a value from 2 to 4094. Any given switch port can be assigned to a specific VLAN, regardless of the physical location of the switch. Different ports on the same switch can be assigned to different VLANs. Each VLAN is a separate layer 2 domain. Traffic sent between VLANs that are connected or mapped to a layer 3 entity, such as a router with subnet interfaces, must traverse the layer 3 device to be forwarded. This means that the segmentation enforced by VLANs at layer 2 can be mapped to logical divisions defined by IP subnets at layer 3.
Description:
A router or layer 3 switch is connected to a border router or firewall via an inline proxy firewall that has a subnet 101.128. In the diagram above, the access block for client devices uses 2 VLANs to segment workstation computer hosts, VLAN 32, from Voice over Internet Protocol, VoIP, handsets, VLAN 40. The VLANs map to 2 subnets, 10.1.32, 0/24 and 10.1.40, 0/24. A VoIP handset with IP address 1.40.100 would need to use a router to contact a computer host with IP 1.1.32.100. The 2 hosts might be connected to the same switch, but the VLAN configuration prevents them from communicating with one another directly. Additionally, an access control rule configured on the router could prevent this type of communication if it were deemed a risk to security. The VLAN topology can be extended across multiple switches. Consider the scenario where the office expands to a second floor, which requires an additional switch appliance to provision sufficient ports. The same VLAN IDs and subnets could be configured for floor 2, making devices on the 2 floors part of the same 2 workstation and VoIP segments. Rate your
Security zones.
The network architecture features that create segments mapped to subnets allow the creation of a zone-based security topology. On-premises networks have a clear organizational boundary at the network perimeter. Hosts outside the perimeter are in a public internet zone and are untrusted. Hosts within the perimeter will have different levels of trust and access control requirements. To map out the internal security topology, analyze the systems and data assets that support workflows and identify ones that have similar access control requirements. Database and file systems that host company data and personal data should prioritize confidentiality and integrity. Data should not usually be held within a single zone, however. Think about the impact when a zone is compromised. If a single zone stores all types of data assets, the impact will be extremely high. Separating different kinds of information into different zones will reduce the breach's impact. Client devices need to prioritize integrity and availability. These devices should not store data and therefore have a lower confidentiality requirement. Public-facing application servers, web, email, remote access, and so on should also prioritize integrity and availability. They should not store sensitive data, such as account credentials. Publicly accessible servers must not be considered fully trusted. Application servers that support the network infrastructure, authentication, directory, and monitoring/logging, for example, must exhibit high levels of confidentiality, integrity, and availability. Any compromise of these services could have catastrophic impacts. This analysis will generate a list of the security zones needed. The network architecture and security control infrastructure must ensure that these zones are segregated from one another by physical and/or logical segmentation. Traffic between zones should be strictly controlled using a security device, typically a firewall. Traffic policies should apply the principle of least privilege. Hosts are trusted in the sense that they are under administrative control and subject to the security mechanisms, antivirus software, user rights, software updating, and so on that have been set up to defend the network. A zone must have a known entry and exit point. For example, if the only authorized access point for a zone is a router, placing a wireless access point within the zone would be a security violation.
Description.
A router or Layer 3 switch is connected to a border router or firewall via an inline proxy firewall that has a subnet 1.128.0/24. It is also connected to 3 access switches. The first access switch has a subnet 10.1.48.0/24 and is connected to printers. The second access switch is connected to workstations and VoIP handsets. The router is connected to VLAN 32 via 10.1.32.0/24 and the access switch. It is also connected to VLAN 40 via 10.1.40.0/24 and the access switch. The third access switch is connected to the private app and database servers. The router is connected to VLAN 16 via 10.1.16.0/24 and switch. It is also connected to VLAN 24 via 1.0.1.24.0/24 and the access switch. The border router or firewall is connected to 2 access switches. The first switch that has a subnet 192.168.42.0/24 is connected to a Wi-Fi access point, which, in turn, is connected to the guest network. The second switch that has a subnet 172.16.0/24 is connected to public app servers. The security zones are as follows. Zone 1, low privilege, printers. Zone 2, medium privilege, workstations and VoIP handsets. Zone 3, untrusted, guest network and public app servers. Zone 4, internet. Zone 5, high privilege, private app and database servers. The traffic between different privilege zones with respect to access controls are as follows. Low privilege zone accepts most new connections, default accept, from medium privilege zone. Medium privilege zone prevents new connections, block all, from low privilege zone. The subnet 10.1.32.0/24 prevents new connections from the subnet 10.1.40.0/24 and vice versa. The subnet 10.1.16.0/24 prevents new connections from the subnet 10.1.240/24. The subnet 10.1.24.0/24 accepts most new connections from the subnet 10.1.16.0/24. The medium privilege zone prevents new connections from the internet. The internet accepts some new connections, default block, from the medium privilege zone. The medium privilege zone prevents new connections from the high privilege zone. The high privilege zone accepts some new connections from the medium privilege zone. One of the ports of the border router or firewall connected to the inline proxy firewall prevents new connections from the untrusted zone. The untrusted zone prevents new connections from the border router. One of the ports of the border router associated with the subnet 192.168.42.0/24 prevents new connections from the internet, and the internet accepts most new connections from this port. One of the ports of border router associated with the subnet 172.168.0/24 accepts most new connections from the internet, and the internet prevents new connections from this port. Network diagram showing security zone privilege levels and simplified access rules. The diagram illustrates how traffic between hosts in zones with different privilege sensitivities can be subject to access controls. A low privilege zone containing hosts that are difficult to secure and patch, such as printers, can accept connections but cannot initiate requests to any other hosts. Client devices on the enterprise LAN can make authorized requests in different zones, such as to internal servers or internet websites, but cannot accept new connection requests. Hosts in a guest zone can access the internet, but are not allowed to access the enterprise LAN. Public-facing servers can accept requests from the internet, but cannot initiate requests to the enterprise LAN or to the internet. Where hosts are separated by VLANs within the same zone, additional access rules can be configured. For example, app servers should be able to make requests to databases, but not vice versa. Rate attack surface. The network attack surface is all the points at which a threat actor could gain access to hosts and services. It is helpful to use the layer model to analyze the potential attack surface. Layer 1/2 allows unauthorized hosts to connect to wall ports or wireless networks and communicate with hosts within the same broadcast domain. Layer 3 allows unauthorized hosts to obtain a valid network address, possibly by spoofing, and communicate with hosts in other zones. Layer 4.7 allows unauthorized hosts to establish connections to TCP or UDP ports and communicate with application layer protocols and services. Additionally, you should consider the external/public attack surface separately from the internal/private attack surface. Each layer requires its own type of security controls to prevent, detect, and correct attacks. Provisioning multiple control categories and functions to enforce multiple layers of protection is referred to as defense in depth. Security controls deployed to the network perimeter are designed to prevent external hosts from launching attacks at any network layer. The division of the private network into segregated zones is designed to mitigate risks from internal hosts that have either been compromised or that have been connected without authorization. Weaknesses in the network architecture make it more susceptible to undetected intrusions or to catastrophic service failures. Typical weaknesses include the following: single points of failure, a pinch point, relying on a single hardware server or appliance or network channel. Complex dependencies, services that require many different systems to be available. Ideally, The failure of individual systems or services should not affect the overall performance of other network services. Availability over confidentiality and integrity. Often it is tempting to take shortcuts to get a service up and running. Compromising security might represent a quick fix, but creates long-term risks. Lack of documentation and change control. Network segments, appliances, and services might be added without proper change control procedures, leading to a lack of visibility into how the network is constituted. It is vital that network managers understand business workflows and the network services that underpin them. Overdependence on perimeter security. If the private network architecture is flat, that is, if any host can contact any other host, penetrating the network edge gives the attacker freedom of movement. Rate your port security. Each wall port and switch port represents an opportunity for a threat actor to attach a device to the network. A threat actor who can operate a host with physical access to a network segment can launch a variety of attacks. Access to the physical switch ports and switch hardware should be restricted to authorized staff. To accomplish this, place the switch appliances in secure server rooms and/or lockable hardware cabinets. To prevent the attachment of unauthorized client devices at unsecured wall ports, the switch port that the wall port cabling connects to can be administratively disabled, or the patch cable can be physically removed from the switch port. Completely disabling ports in this way can introduce a lot of administrative overhead and allow room for error. Also, it doesn't provide complete protection, as an attacker could unplug a device from an enabled port and connect their own machine. Consequently, more sophisticated methods of ensuring port security have been developed. MAC filtering and MAC limiting. The network adapter in each host computer is identified by a MAC address. Configuring MAC filtering means a switch port only permits certain MAC addresses to connect. This can be done by creating a list of valid MAC addresses or by specifying a limit to the number of permitted addresses. For example, if port security is enabled with a maximum of 2 MAC addresses, the switch will record the first 2 MACs to connect to that port. The switch then drops any traffic from machines with different MAC addresses that try to connect. Configuring ARP inspection on a Cisco switch. Courtesy of Cisco Systems Incorporated, unauthorized use not permitted. 802.1x and Extensible Authentication Protocol. Restricting access by MAC address is difficult to manage and still prone to spoofing. Better security is obtained by forcing computers and/or users to authenticate before full network access is granted. The IEEE 802.1x Port-Based Network Access Control (PNAC) standard allows a switch to require authentication when a host connects to one of its ports. 802.1x uses authentication, authorization, and accounting AAA architecture. Supplicant is the device requesting access, such as a user's PC or laptop. Authenticator is the switching device or any type of network access appliance. This does not validate authentication requests directly, but acts as a conduit for authentication data. Authentication server, the server that holds or can contact a directory of network objects and that can validate authentication requests, issue authorizations, and perform accounting of security events. The 802.1x standard is implemented by 2 protocols. Extensible Authentication Protocol, EAP, provides a framework for deploying multiple types of authentication methods. It is often used with digital certificates to establish a trust relationship and create a secure tunnel to transmit the user credential or to perform smart card authentication without a password. Remote Authentication Dial-In User Service, RADIUS, allows the authenticator and authentication server to communicate authentication and authorization decisions. The authenticator is a RADIUS client. The authentication server is a RADIUS server. When a host connects to an 802.1x enabled switch port, the switch opens the port for the EAP over LAN, EAPRL, protocol only. The switch port only allows full data access when the host has been authenticated. The switch receives an EAP packet with the supplicant's credentials. These are encrypted and cannot be read by the switch. The switch uses the RADIUS protocol to send the EAP packet to the authentication server. The authentication server can access the directory of user accounts and can validate the credential. If authentication is successful, it informs the switch that full network access can be granted. Description. The steps are as follows. 1. The Radius server and client are preconfigured with the same shared secret. 2. The supplicant connects to the network. 3. The switch enables EAPL and instructs the supplicant to authenticate. 4. The supplicant transmits EAP data. 5. The switch encrypts the EAP data using the shared secret and forwards it to the Radius server. 6. The Radius server decrypts the packet using the shared secret and validates the credential. 7. The Radius server issues an access accept. 8. The switch decrypts the access accept and opens the network channel for regular traffic. IEEE 802.
Authentication's kind of been the problem of our age. We have to figure out technical ways to really figure out when somebody asserts that they are who they are, or if a machine or a process asserts what they are. How can we really figure that out? How do we determine friend from foe? Well, when it comes to configuring authentication technologies, we have the extensible authentication protocol. And it really enables the AAA. And by the AAA, I don't mean the insurance folks if you're from the US or whatever. I'm talking about authentication, authorization, and accounting. Let me see if I can explain that. So identification is simply where you are actively proving the identity of some sort of process or a person, and even the condition of the user. You could call that user a supplicant. You could call that user a subject. But the whole idea is to figure out actively how to identify something. And that's much more than just defining a username and then logging it when that person logs in. It's much more sophisticated. So with authentication, it's the whole idea that you're really proving what the subject or the person or thing asking really is. With authorization, that's where you basically determine, okay, here's the state of the subject or the supplicant. And by state, I mean, what's the condition of the computer that's logging in? Where's the location? That sort of thing. And then it authorizes specific access to services. And then accounting is basically what happened. And how accurately is your accounting? So think of it this way. We've all heard of IRS audits or whatever in the United States anyway. In the cybersecurity world, that kind of auditing has gotten much more serious because we, for too long, have not enabled auditing properly. Because we haven't really tracked and recorded what the subject used and what the conditions were. So one of the ways to talk about the AAA here is basically as somebody is identified or as a process is identified. You can call it the owner or what have you, but the user then authenticates. After authentication comes authorization, and all the while comes accounting. So accounting is not just done at the end, it's handled all the way through. It's a really important thing to understand. A major part of this is the extensible authentication protocol. And EAP is very interesting because it contains three major parts. So as you go to access a network resource, you're basically a supplicant. It could be a machine, it could be a person. We'll talk about it in terms of a device. And this device is something that it has to authenticate itself or else it's not allowed to get further access. And so it basically goes to something called attaches to an authenticator. The authenticator could be a switch, it could be a network access point that will allow or disallow access, but it doesn't make that decision in terms of authentication itself. It will then go to an authentication server. That's the third part. And this often is a Radius server. And the idea is that it manages the authentication information. So the authenticator and the authentication service compute, they work with each other. And if that device, person, whatever is allowed, then they have access to network resources. When it comes to EAP services, there are quite a few things here. The extensible authentication protocol over LAN, EPOL, is basically allows you to authenticate specific ports and specific even physical ports on a machine. It uses the 802.1x protocol. And it basically gives a way for sign-ons to occur. It's not vendor specific. People will call it a generic sign-on for network resources. Another way to do this, there are various key management devices that can be used. You can use a smart card. You can even use something like it looks like a USB. It's in the same form factor, a USB drive. It's not a USB drive, but it's in the same form factor. Or you could use a trusted computing module. I took a picture here of such a module. You can grab one of those, and oftentimes they get embedded in some sort of computing device. So the idea is that you're using these services to enhance authentication, to truly identify what a supplicant is, or what a subject is, or what a device is doing.
Physical isolation. Some hosts are so security critical that it is unsafe to connect them to any type of network. One example is the Root Certification Authority in PKI. Another example is a host used to analyze malware execution. A host that is not physically connected to any network is said to be air-gapped. It is also possible to configure an air-gapped network. This means that hosts within the air-gapped network can communicate, but there is no cabled or wireless connection to any other network. Military bases, government sites, and industrial facilities use air-gapped networks. Physically isolating a host or a group of hosts improves security, but also incurs significant management challenges. Device administration has to be performed at a local terminal. Any updates or installs have to be performed using USB or optical media. This media is a potential attack vector and must be scanned before allowing its use on an air-gapped host. Rate your confidence. Architecture considerations. When evaluating the use of a particular architecture and selecting effective controls, consider a number of factors. Cost, like architecture changes and the acquisition and upgrade of appliances and software require an upfront capital outlay, which can depreciate and lose value. There are also ongoing maintenance and support liabilities. The value of the investment in security architecture and controls can be calculated based on how much they reduce losses from incidents. Compute and responsiveness. Minimize processing time for workloads. A workload is the processing effort required to complete a task, such as a web server responding to a client request. Each network device requires sufficient CPU, system memory, storage, and network bandwidth resources to ensure an acceptable response time for a given workload. Higher compute resources incur greater costs. Scalability and ease of deployment. Minimize costs when workloads increase or decrease. If workloads decrease, it can be difficult to recover capital costs. If workloads increase, it can be difficult to deploy new nodes or upgrade existing nodes to maintain responsiveness. A scalable system is one that can quickly or automatically add or remove compute resources without incurring excessive costs. Availability minimizes downtime or maximizes uptime. Downtime represents the loss of opportunity to do work, damaging the business's reputation, revenue, and profitability. Downtime can be due to planned maintenance or unplanned failures and security incidents. Resilience and ease of recovery reduce the time to recover from a failure. For example, a system that recovers from a failure without manual intervention is more resilient than one that requires an administrator to restart it. Power is a feature that ensures the facility can meet the energy demands of its devices and workloads. Resources increases costs. Ensuring that the building infrastructure minimizes power failures improves availability. Patch availability ensures that firmware and software code is protected against exploits for known vulnerabilities. Conversely, the network owner cannot manage this process when they rely on a third party to maintain infrastructure or when a device or software product is no longer supported by its vendor. Risk transference is a contract that uses a third party to manage the network infrastructure. A service level agreement, SLA, can be defined with penalties if metrics for responsiveness, scalability, availability, and resilience are not maintained. On-premises networks tend to have high capital costs and low scalability. For example, consider the difficulty of increasing bandwidth from 1 gigabit per second to 10 gigabits per second operation across the entire site. This would likely require the installation of new cable throughout the building. Recovery procedures can be complex if the site premises is affected by a large-scale disaster. This means that availability and resilience can be lower than alternative solutions such as cloud networking. Rate your confidence.
Continue.
Exam objectives covered. 3.2 given a scenario, apply security principles to secure enterprise infrastructure. Given a zone-based network security architecture, network security appliances ensure traffic that flows between and within zones meets access control policies. The selection of controls based on their functions and attributes and their appropriate placement within the topology is critical to ensuring effective network security. This topic will help you to understand the considerations that must be made when designing a security solution for a given scenario. Rate. Device placement. The selection of effective controls for network infrastructure is the process of choosing the type and placement of security appliances and software. The aim is to enforce segmentation, apply access controls, and monitor traffic for policy violations. The selection of effective controls is governed by the principle of defense in depth. Defense in depth means that security-critical zones are protected by diverse preventive, detective, and corrective controls operating at each layer of the OSI model. Defense in depth is ensured through careful selection of device placement within the network topology. There are 3 options. Preventive controls are often placed at the border of a network segment or zone. Preventive controls, such as firewalls, enforce security policies on traffic entering and exiting the segment, ensuring confidentiality and integrity. A load balancer control ensures high availability for access to the zone. Detective controls might be placed within the perimeter to monitor traffic exchanged between hosts within the segment. This provides alerting of malicious traffic that has evaded perimeter controls. Corrective controls might be placed within the traffic to correct detected errors or irregularities. Preventive, detective, and corrective controls might be installed on hosts as a layer of endpoint protection in addition to the network infrastructure controls. Description: a router or layer 3 switch is connected to a border router or firewall. The router or layer 3 switch is connected to 3 access switches. The first access switch has a subnet 10.1.48.0/24 and is connected to printers. The second access switch is connected to workstations and VoIP handsets. The router is connected to VLAN 32 via 1.0.132.0/24 and the access switch. It is also connected to VLAN 40 via 10.1.40.0/24 and the access switch. The third access switch is connected to the private app and database servers. The router is connected to VLAN 16 via 10.1.1.6.0/24 and the access switch. It is also connected to VLAN 24 via 10.1.2.4.0/24 and the access switch. The border router or firewall is connected to 2 access switches. The first switch that has a subnet 192.168.42.0/24 is connected to a Wi-Fi access point, which, in turn, is connected to the guest network. The second switch that has a subnet 172.16.0/24 and is connected to public app servers. The placement of different security controls is as follows. 1. Preventive control at the border router. 2. Detective control in the connection between router and firewall. 3. Preventive control at router or layer 3 switch. 4. Corrective control at untrusted zones. 5. Detective controls at the third access switch. 6. Detective, corrective, and preventive control at VLAN 32. Detective, corrective, and preventive control are also placed at VLAN 16 and connection between the access point and public app servers. Placement of security controls to ensure diversity and defense in depth. As an illustration, the diagram shows how different control types can be positioned within the network to ensure defense in depth. At the network border, a preventive control such as a firewall enforces access rules for ingress and egress traffic. A sensor placed inline behind the border firewall relays traffic to an intrusion detection system to implement detective control and identify malicious traffic that has evaded the firewall. Access control lists configured on internal routers enforce rules for traffic being forwarded between internal zones and hosts. Incoming traffic for public-facing servers can be mediated by a load balancer, providing a corrective control to mitigate denial of service attacks. Sensors attached to mirrored switch ports enable intrusion detection for the most sensitive privilege level hosts or zones. On each host, endpoint protection software applies a range of preventive, detective, and corrective controls to mitigate threats that have evaded network controls. Endpoint software can implement host firewalls, antivirus, intrusion detection, and data loss prevention. Rate your device attributes. Attributes determine the precise way in which a device can be placed within the network topology. Active versus passive. A passive security control is one that does not require any sort of client or agent configuration or host data transfer to operate. For example, network traffic can be directed or copied to a sensor and scanned by an analysis engine. This control is completely passive. Hosts on the network would be unaware that it is operating. The control has no addressable interface. An active security control that performs scanning must be configured with credentials and access permissions and exchange data with target hosts. An active control that performs filtering requires hosts to be explicitly configured to use the control. This might mean installing agent software on the host or configuring network settings to use the control as a gateway. Inline devices and monitor methods. A device that is deployed inline becomes part of the cable path. No changes in the IP or routing topology are required. The device's interfaces are not configured with MAC or IP addresses. An inline device can copy network traffic to a monitor or sensor. The sensor can be configured to receive traffic in two different ways. Test Access Point, TAP. This is an inline device with ports for incoming and outgoing network cabling and an inductor or optical splitter that physically copies the signal from the cabling to a monitor port. There are types for copper and fiber optic cabling. As a physical layer hardware solution, no logic decisions are made, so the monitor port receives every frame, corrupt or malformed or not, and the copying is unaffected by load. SPAN, Switched Port Analyzer, /mirror port. This means that the sensor is attached to a specially configured mirror port on a switch that receives copies of frames addressed to nominated access ports, or all the other ports. This method is not completely reliable. Frames with errors will not be mirrored, and frames may be dropped under heavy load. A tap device is placed inline with the cable path, while a mirror port uses the switch to copy frames to a detection system. The router/firewall is an active control as client devices must be configured to use it for internet access. The tap and mirror ports are passive controls. They are completely transparent to the server and client hosts. Fail open versus fail closed. A security device could enter a failure state for a number of reasons. There could be a power or hardware fault, an unreconcilable policy violation, or a configuration error. Hardware failure can be caused by power surges, overheating, and physical damage. Software failure can occur because of bugs, security vulnerabilities, and compatibility issues. Configuration issues can be caused by human errors such as inattention, fatigue, or lack of training. Finally, devices or sites might be impacted by natural disasters such as floods, hurricanes, and earthquakes. When it fails, a device can be designed or configured to fail open or fail closed. Fail open means that network or host access is preserved if possible. This mode prioritizes availability over confidentiality and integrity. The risk of a fail-open control is that a threat actor could engineer a failure state to defeat the control. Fail-closed means that access is blocked or that the system enters the most secure state available, given whatever failure occurred. This mode prioritizes confidentiality and integrity over availability. The risk of a fail-closed control is system downtime. It may or may not be possible to configure the fail mode. For example, an inline security appliance that suffers power failure will fail closed unless there is an alternative network path. Some devices designed to be installed inline have a backup cable path that will allow a fail-open operation. Rate your confidence. Firewalls. A firewall is a preventive control designed to enforce policies on traffic entering and exiting a network zone. Packet filtering. A packet filtering firewall is configured by specifying a group of rules called an Access Control List, ACL. Each rule defines a specific type of data packet and the action to take when a packet matches the rule. A packet filtering firewall can inspect the headers of IP packets. Rules are based on the information found in those headers. IP filtering accepts or denies traffic based on its source and/or destination IP address. Most firewalls can filter by MAC addresses. Protocol ID/type is an IP packet that carries an identified protocol. Most commonly, this is either TCP or UDP data. Other types include Internet Control Message Protocol, ICMP, diagnostic traffic, and protocols that facilitate routing. Port filtering/security accepts or denies a packet based on the source and destination TCP/UDP port numbers. If the action is configured to accept or permit, the firewall allows the packet to pass. A drop or deny action silently discards the packet. A reject action blocks the packet, but responds to the sender with an ICMP message, such as port unreachable. Separate ACLs filter inbound and outbound traffic. Controlling outbound traffic can block applications not authorized to run on the network and defeat malware such as backdoors. Firewall device placement and attributes. Firewalls can be implemented as various types of hardware appliances or as software running on a general computing host. Some types of firewalls are better suited for placement at the network edge or zonal borders. Others are designed to protect individual hosts. An appliance firewall is a standalone hardware firewall deployed to monitor traffic passing into and out of a network zone. An appliance firewall can be deployed in 3 ways. Routed Layer 3. The firewall performs forwarding between subnets. Each interface on the firewall connects to a different subnet and represents a different security zone. Each interface is configured with an IP and MAC address. Bridged Layer 2. The firewall inspects traffic passing between 2 nodes, such as a router and a switch. It bridges the Ethernet interfaces between the 2 nodes, working like a switch. Despite performing forwarding at Layer 2, the firewall can still inspect and filter traffic on the basis of the full range of packet headers. The firewall's interfaces are configured with MAC addresses, but not IP addresses. Inline Layer 1. The firewall acts as a cable segment. The 2 interfaces don't have MAC or IP addresses. Traffic received on one interface is either blocked or forwarded over the other interface. This is also referred to as virtual wire or bump in the wire. Both bridged and inline firewall modes can be referred to as transparent modes. The typical use case for a transparent mode is to deploy a firewall without having to reconfigure subnets and reassign IP addresses on other devices. For example, you could deploy a transparent firewall in front of a web server host without having to change the host's IP address. Alternatively, this type of firewall could be placed between a router and a switch. A transparent firewall needs an additional interface for management and configuration. This does have an IP address. A routed firewall can either have a dedicated management interface or accept management traffic on any interface. Using a dedicated management interface is more secure. Description. The dashboard shows the OpenSense logo on the top left, followed by a web address, which is followed by a search bar. The menu on the left has tabs: Lobby, Reporting, System, Interfaces, Firewall, VPN, Services, Power, and Help. The tab Lobby has sub-options Dashboard selected, License, Password, and Logout. The head Lobby dashboard is followed by the Save Settings selected and Add Widget button on the right. A drop-down on the further right reads, 2 columns. The box on the left below provides system information such as name, versions, updates, CPU type, CPU usage, load average, uptime, current date or time, last config change, and CPU usage. The boxes on the right are titled, services, gateways, interfaces, and traffic graph. Gateways box lists name, RTT, RTTD, loss, and status. The traffic graph box shows a graph. Status dashboard for the OpenSense open source security platform. Screenshot courtesy of OpenSense. A router firewall or firewall router appliance implements filtering functionality as part of the router firmware. The difference is that a router appliance is primarily designed for routing, with a firewall as a secondary feature. Small office/home office, SOHO. Internet routers/modems come with a firewall built-in, for example. Rate your confidence.
Confidence.
Continue. A router firewall or firewall router appliance implements filtering functionality as part of the router firmware. The difference is that a router appliance is primarily designed for routing, with a firewall as a secondary feature. Small office/home office, SOHO. Internet routers/modems come with a firewall built-in, for example. Rate your confidence. Layer 4 and Layer 7 firewalls. A basic packet filtering firewall is stateless. This means that it does not preserve information about network sessions. Each packet is analyzed independently, with no record of previously processed packets. This type of filtering requires the least processing effort, but it can be vulnerable to attacks spread over a sequence of packets. A stateless firewall can also introduce problems in traffic flow, especially when using some sort of load balancing or when clients or servers need to use dynamically assigned ports. A stateful inspection firewall tracks information about the session established between two hosts. All firewalls now incorporate some level of stateful inspection capability. Session data is stored in a state table. When a packet arrives, the firewall checks it to confirm whether it belongs to an existing connection. If it does not, it applies the ordinary packet filtering rules to determine whether to allow it. Once the connection has been allowed, the firewall usually allows traffic to pass unmonitored in order to conserve processing effort. Description. On the right of the title is a drop-down to select rule. Below the title are 2 tabs, States selected, and Actions. The States tab has a search box, a refresh button, and 2 drop-downs on the top right. The data are provided in a table format whose headers read int, dir, proto, source, nat, destination, state, rule, and commands. The status bar at the bottom reads, showing 1 to 7 of 74 entries. State table in the OpenSense firewall appliance. Screenshot courtesy of OpenSense. Stateful inspection can occur at Layer 4 and Layer 7. Layer 4 firewall. Layer 4 is the OSI transport layer. A Layer 4 firewall examines the TCP three-way handshake to distinguish new from established connections. A legitimate TCP connection should follow a SYN/ACK sequence to establish a session, which is then tracked using sequence numbers. Deviations from this, such as SYN without ACK or sequence number anomalies, can be dropped as malicious flooding or session hijacking attempts. The firewall can be configured to respond to such attacks by blocking source IP addresses and throttling sessions. It can also track UDP traffic, though this is harder as UDP is a protocol without connections. It is also likely to be able to detect IP header and ICMP anomalies.
Description.
The firewall adaptive timeouts has 2 boxes to enter the start and end values, respectively. The text below describes the input of the boxes. The firewall maximum states box has a box to enter the maximum number of connections to hold in the firewall state table. OpenSense firewall rule configuration Advanced settings allow maximums for states and connections to be applied. Screenshot courtesy of OpenSense. Layer 7 Firewall. A Layer 7 firewall can inspect the headers and payload of application layer packets. One key feature is to verify the application protocol matches the port, because malware can try to send raw TCP data over port 80 just because port 80 is open, for instance. As another example, a web application firewall could analyze the HTTP headers and the web page formatting code present in HTTP packets to identify strings that match a pattern in its thread database. Application-aware firewalls have many different names, including application layer gateway, stateful multi-layer inspection, and deep packet inspection. Application-aware devices have to be configured with separate filters for each type of traffic: HTTP and HTTPS, SMTP/POP/IMAP, FTP, and so on. Rate your confidence. Continue.
Category.
Proxy servers. A firewall that performs application layer filtering is likely implemented as a proxy. Where a network firewall only accepts or blocks traffic, a proxy server works on a store and forward model. The proxy deconstructs each packet, performs analysis, then rebuilds the packet and forwards it on, providing it conforms to the rules. The amount of rebuilding depends on the proxy. Some proxies only manipulate the IP and TCP headers. Application-aware proxies might add or remove HTTP headers. A deep packet inspection proxy might be able to remove content from an HTTP payload. Forward proxy servers. A forward proxy provides for protocol-specific outbound traffic. For example, a web proxy enables client computers on the local network to connect to websites and secure websites on the internet. This is a forward proxy that services TCP ports 80 and 443 for outbound traffic.
Description.
The sub-option, Administration, is selected under the tab Web Proxy from the left menu. The right pane shows 4 tabs from which Forward Proxy is selected. Boxes to type the subnet addresses for the heads allowed subnets, unrestricted IP addresses, banned host IP address, whitelist, and blacklist are given below. The box for banned host IP address reads 2030.113.66, and that for blacklist reads example.com. A clear all and copy option is given below each box. An apply button is at the bottom left. Configuring filter settings for the caching proxy server running on OpenSense. The filter can apply ACLs to prohibit access to IP addresses and URLs. Screenshot courtesy of OpenSense. The main benefit of a proxy is that client computers connect to a specified point on the perimeter network for web access. This provides a degree of traffic management and security. In addition, most web proxy servers provide caching engines, whereby frequently requested web pages are retained on the proxy, negating the need to refetch those pages for subsequent requests. A proxy server must understand the application it is servicing. For example, a web proxy must be able to parse and modify HTTP commands and, potentially, web page code and scripts too. Some proxy servers are application-specific, others are multipurpose. A multipurpose proxy is one configured with filters for multiple protocol types, such as web data, file transfer protocol data, and email protocol data. Proxy servers can generally be classed as non-transparent or transparent. A non-transparent proxy means the client must be configured with the proxy server address and port number to use it. By convention, the port on which the proxy server accepts client connections is often configured as port TCP/8080. A transparent, or forced or intercepting, proxy intercepts client traffic without the client having to be reconfigured. A transparent proxy must be implemented as a router or as an inline network appliance. Description. The sub-option, Administration, is selected under the tab Web Proxy from the left menu. The right pane shows 4 tabs from which Forward Proxy is selected. The fields are as follows.
Proxy interface, GUID, LAN.
Proxy port, 3128. Enable transparent HTTP proxy. Checkbox selected. Enable SSL inspection. Checkbox selected. Log SNI information only. Checkbox not selected. SSL proxy port 3129. CA to use. Drop-down with Structurality Proxy Services CA selected.
SSL no bump sites .google.com, .bing.com, .structurality.com.
Configuring transparent proxy settings for the proxy server running on OpenSense. The proxy uses its own certificate to intercept secure connections and inspect the URL. Screenshot courtesy of OpenSense. Both types of proxy can be configured to require users to be authenticated before allowing access. The proxy is likely to be able to use single sign-on SSO to do this without having to prompt the user for a password. A proxy auto-configuration (PAC) script allows a client to configure proxy settings without user intervention. The Web Proxy Auto Discovery (WPAD) protocol allows browsers to locate a PAC file. Reverse proxy servers. A reverse proxy server provides for protocol-specific inbound traffic. A reverse proxy is typically deployed on the network edge and configured to listen for client requests from a public network, the Internet. The proxy applies filtering rules, and if accepted, it creates the appropriate request and forwards it to an application server within a specially secured screened subnet zone on the local network. Rate your Intrusion detection systems. An intrusion system is a control that performs real-time analysis of either network traffic or system and application logs. Sensors. A network intrusion system captures traffic via a packet sniffer, referred to as a sensor. The sensor could use a span/mirror port or an inline tap. Typically, the packet capture sensor is placed behind a firewall or close to a server of particular importance. The idea is usually to identify malicious traffic that has managed to get past the firewall. A single sniffer can record a large amount of traffic data, so you cannot put multiple sensors everywhere in the network without provisioning the resources to manage them properly. Depending on network size and resources, one or a few sensors are deployed to monitor key assets or network paths. Intrusion detection systems. The traffic captured by each sensor is transferred to a host or appliance running an intrusion detection system, IDS, such as Snort, Snort.org, Suricata, Suricata.io, or Zeek/Bro, Zeek.org. When traffic matches a detection signature or heuristic pattern, the IDS raises an alert or generates a log entry, but does not block the source host. This type of passive sensor does not slow down traffic and is undetectable by the attacker. An IDS is used to identify and log hosts and applications and to detect password guessing attempts, port scans, worms, backdoor applications, malformed packets or sessions, and other policy violations.
Description.
The Kibana logo is on the top left. Discover option is selected from the menu on the left. The right pane has two sections. The top section shows the time and source, and the bottom section has tabs, table, selected, and JSON. It provides information on timestamp, version, ID, index, score, type, alert, category, classification, and destination_geo.continent_code. Viewing an intrusion detection alert generated by Snort in the Kibana app on Security Onion. Screenshot courtesy of Security Onion https://securityonionsolutions.com. Intrusion prevention systems. An intrusion prevention system, IPS, is an appliance or software capable of an active response. An IPS scans traffic to match detection signatures, and it can be configured to automatically act to stop an attack. The following responses are typical. Block the source of the non-compliant traffic, either temporarily or permanently. This is referred to as shunning. Reset the connection, but do not block the source address. Redirect traffic to a honeypot or honeynet for additional threat analysis. An IPS can be deployed as an inline appliance with an integrated firewall and routing/forwarding capability. If deployed with a passive sensor, it can implement the response action by reconfiguring another appliance, such as a firewall or a router. This functionality uses a script or application programming interface, API, to integrate the two security controls. Rate your next-generation firewalls, and unified threat management. While intrusion detection was originally produced as standalone software or appliances, its functionality quickly became incorporated into a new generation of firewalls. The original next-generation firewall, NGFW, was released in 2010 by Palo Alto. There is no official specification for what an NGFW can do, but the following features are typical. Layer 7 application-aware filtering, including inspection of transport layer security, TLS, encrypted traffic. Integration with network directories, facilitating per-user or per-role content and time-based filtering policies, providing better protection against an insider threat. Intrusion Prevention System, IPS, functionality. Next-generation firewalls can combine traditional firewall functionalities with advanced capabilities, such as deep packet inspection, intrusion prevention, and application awareness. Integration with cloud networking. Unified Threat Management, UTM, refers to a security product that centralizes many types of security controls: firewall, anti-malware, network intrusion prevention, spam filtering, content filtering, data loss prevention, virtual private networking, VPN, cloud access gateway, and endpoint protection/malware scanning into a single appliance. This means monitoring and management of diverse controls are consolidated into a single console. Nevertheless, UTM has some downsides. When a defense is unified under a single system, this creates the potential for a single point of failure that could affect an entire network. Distinct security systems, if they fail, might only compromise that particular avenue of attack. Additionally, UTM systems can struggle with latency issues if subject to high levels of network activity. Also, a UTM might not perform as well as software or a device with a single dedicated security function. To some extent, NGFW and UTM are just marketing terms. UTM is commonly deployed in small and medium-sized businesses that require a comprehensive security solution but have limited resources and IT expertise. A UTM is seen as a turnkey, do-everything solution, while a NGFW is an enterprise product with fewer features but better performance. Rate your Load balancers. A load balancer distributes client requests across available server nodes in a farm or pool. This is used to provision services that can scale from light to heavy loads and to provide mitigation against denial of service attacks. A load balancer also provides fault tolerance. If there are multiple servers available in a farm all addressed by a single name/IP address via a load balancer, then if a single server fails, client requests can be forwarded to another server in the farm. A load balancer can be deployed in any situation where there are multiple servers providing the same function. Examples include web servers, front-end email servers, web conferencing, video conferencing, and streaming media servers. There are two main types of load balancers. Layer 4 load balancer. Basic load balancers make forwarding decisions on IP address and TCP/UDP port values, working at the transport layer of the OSI model. Layer 7 load balancer, content switch. As web applications have become more complex, modern load balancers need to be able to make forwarding decisions based on application-level data, such as a request for a particular uniform resource locator, URL, web address, or data types like video or audio streaming. This requires more complex logic, but the processing power of modern appliances is sufficient to deal with this. Description. The 3 steps are as follows. 1. Client connects to the virtual server over the internet. 2. The load balancer selects a web server instance to handle the connection and forwards the traffic. 3. A persistence mechanism can keep the client connected to the same server if it is available. Topology of basic load balancing architecture. Images copyright 123rf.com. Scheduling. The scheduling algorithm is the code and metrics that determine which node is selected for processing each incoming request. The simplest type of scheduling is called round-robin. This means picking the next node. Other methods include picking the node with the fewest connections or the best response time. Each method can be weighted using administrator set preferences or dynamic load information, or both. The load balancer must also use some type of heartbeat or health check probe to verify whether each node is available and under load or not. Layer 4 load balancers can only make basic connectivity tests, while Layer 7 appliances can test the application state and verify host availability. Source IP affinity and session persistence. When a client device has established a session with a particular node in the server farm, it may be necessary to continue to use that connection for the duration of the session. Source IP or session affinity is a Layer 4 approach to handling user sessions. It means that when a client establishes a session, it becomes stuck to the node that first accepted the request. An application layer load balancer uses persistence to keep a client connected to a session. Persistence typically works by setting a cookie either on the node or injected by the load balancer. This can be more reliable than source IP affinity, but requires the browser to accept the cookie. Rate your confidence.
You know, when it comes to load balancing, you have a lot of choices. And two of the major choices are going to be, do you want it for kind of web traffic, port 80? Do you want it kind of layer 4, as it were, where it has the opportunity for load balancing for additional protocols? I've got here load balancer options open here in AWS. So you can either do your application load balancing, and by application, they're talking about web applications. A lot of the middleware, let's say, a lot of the options that are available. And so you can, as I click on here to configure the load balancing, you're basically now talking about provisioning for, in this case, web applications. So I'll just call it Stang Web Apps. That's the name. And I'm going to call it internet facing, because as the idea is that as a lot of load comes in from the internet, I'm going to need to find some way to kind of fork all of these things off, as it were. I shouldn't use that word fork, but you're going to basically shift all of that load off into multiple areas. And the load balancing protocol, I can do it either HTTP or I can use secure HTTP. I'm going to choose that. You can also add various listeners here. I'll keep that as HTTP or HTTPS. If you do HTTP, it will listen for HTTP and then bring it on over to HTTPS. But I'm going to keep things secure as they are. Because I happen to be on the East Coast right now, it's giving me options for specific availability zones. That's an important concept when you're provisioning your load balancer. And then you can actually go in, once you're done here, you can specify a couple of subnets. I should remember this. You need to specify at least 2, because the idea of load balancing means that you take that load from one area and then you can bring it into 2 or more subnets. May as well make it all 3. Why not? Be nice if I could actually click next here. There we go. And the tags, and you basically add some tags here. So net1 value, there we go. And the idea is that as you go in and select your configure your security settings, you then have the opportunity to do additional ports here. So let's see here. I'm going to go ahead and change this to HTTP even as we speak. There we go. And you can now set your security settings, and you can get your certificate from various sources. I'm going to go ahead and do it here from Adobe Web Services' existing certificates. And the idea is that as you configure security groups, you have the opportunity to basically do load balancing into secure servers. So this is basically some of the first steps that you'll take as you go ahead and provision your load balancers.
Web Application Firewalls. A Web Application Firewall, WEF, is designed to protect software running on web servers and their backend databases from code injection and denial of service attacks. WEFs use application-aware processing rules to filter traffic and perform application-specific intrusion detection. The WEF can be programmed with signatures of known attacks and use pattern matching to block requests containing suspect code. The output from a WEF will be written to a log, which can reveal potential threats to the web application.
Description.
The sub-option application under the window logs is selected from the menu on the left. The right pane has two sections. The top section titled Application lists the number of events, 12,660. It lists the level, date and time, and source of the application in a tabular format. The bottom section titled Event 1, Mod Security has two tabs, General and Details selected. It has two radio buttons, Friendly View, selected, and XML View. A computer code is written below. With the Mod Security WEF installed to this IIS server, a scanning attempt has been detected and logged as an application event. As you can see, the default rule set generates a lot of events. Screenshot used with permission from Microsoft. A WEF may be deployed as an appliance, protecting the zone that the web server is placed in, or as plugin software for a web server platform. Rate your confidence. Exam objectives covered. 3.2 Given a scenario, apply security principles to secure enterprise infrastructure. With today's mobile workforce, most networks have to support connections by remote employees, contractors, and customers. These connections often use untrusted public networks, such as the Internet. Consequently, understanding how to implement secure communications protocols for virtual networking will be a major part of your job as an information security professional. There are also cases where a user needs to remotely access an individual host. This most commonly allows administrators to remotely manage workstations, servers, and network appliances, but it can also provide ordinary users access to a desktop. Rate your confidence. Remote access architecture. Remote access networking means that the user's device does not make a direct cabled or wireless connection to the network. The connection occurs over or through an intermediate network. Historically, remote access used analog modems connecting over the telephone system. These days, most remote access is implemented as a virtual private network, VPN, running over Internet Service Provider, ISP networks. With a remote access VPN, clients connect to a VPN gateway on the edge of the private network. This client-to-site VPN topology is the telecommuter model, allowing homeworkers and employees working in the field to connect to the corporate network. The VPN protocol establishes a secure tunnel to keep the contents private, even when the packets pass over ISP's routers.
Description.
The remote access screened subnet consists of a VPN gateway and router or firewall, and the local network consists of router or firewall and LAN servers. The steps are as follows. 1. The VPN client host connects to a VPN gateway using any type of Internet subscriber access method. 2. The VPN gateway authenticates the user and creates a secure encrypted tunnel. 3. VPN client traffic is routed over the network and can access authorized services. Remote Access VPN. Images copyright 123rf.com. A VPN can also be deployed in a site-to-site model to connect two or more private networks. Whereas remote access VPN connections are typically initiated by the client, a site-to-site VPN is configured to operate automatically. The gateways exchange security information using whichever protocol the VPN is based on. This establishes a trust relationship between the gateways and sets up a secure connection through which to tunnel data. Hosts at each site do not need to be configured with any information about the VPN. The routing infrastructure at each site determines whether to deliver traffic locally or send it over the VPN tunnel. Description. The site-to-site VPN consists of three components. A branch office that consists of the branch office servers and clients and the router or firewall or VPN gateway. A head office screen subnet that consists of VPN gateway and router or firewall. A head office local network that consists of router or firewall and head office servers. The steps are as follows. 1. The VPN gateway at a branch office establishes a VPN connection with the head office site. 2. Traffic for a host at a remote site is automatically routed and tunneled over the VPN link. Site-to-site VPN. Images copyright 123rf.com. A third topology is a host-to-host tunnel. This is a means of securing traffic between two computers where the private network is not trusted. Several VPN protocols have been used over the years. Legacy protocols such as the Point-to-Point Tunneling Protocol, PPTP, have been deprecated because they do not offer adequate security. Transport Layer Security, TLS, and Internet Protocol Security, IPsec, are now the preferred options for configuring VPN access. Rate your confidence. Transport Layer Security Tunneling. A Transport Layer Security, TLS, VPN means the client connects to the remote access server using digital certificates. The server certificate identifies the VPN gateway to the client. Optionally, the client can also be configured with its own certificate. This allows for mutual authentication, where both server and client prove their identity to one another. TLS creates an encrypted tunnel for the user to submit authentication credentials. These would normally be processed by a radius server. Once the user is authenticated and the connection is fully established, the VPN gateway tunnels all communications for the local network over the secure socket.
Description.
The server's option under the suboption OpenVPN, which is under the head VPN, is selected from the left menu. The right pane is titled General Information. The fields are as follows: Disabled, blank checkbox. Description: Remote Access VPN Server Mode. Remote Access, SSL/TLS plus user off. Backend for authentication. Structurality. Enforce local group. None. Protocol, UDP. Device mode. TUN. Interface, WAN, local port, 1194. Configuring an OpenVPN server in the OpenSense security appliance. This configuration creates a remote access VPN. Users are authenticated via a radius server on the local network. Screenshot courtesy of OpenSense.
Description.
The cryptographic settings are as follows: TLS authentication, enabled authentication and encryption. TLS shared key, checked in checkbox, automatically generate a shared TLS authentication key. Peer certificate authority, structurality enterprise root. Peer certificate revocation list, none. Server certificate, structurality remote access VPN server. Encryption algorithm, deprecated none. Auth digest algorithm, SHA-256, 256-bit. Certificate depth, 1 client plus server. Strict user or CN matching, blank checkbox. Configuring a server certificate for OpenVPN in the OpenSense security appliance. Screenshot courtesy of OpenSense. A TLS VPN can use either TCP or UDP. UDP might be chosen for marginally superior performance, especially when tunneling latency-sensitive traffic such as voice or video. TCP might be easier to use, with a default firewall policy. TLS over UDP is also referred to as datagram TLS, DTLS. It is important to use a secure version of TLS. The latest version at the time of writing is TLS 1.3. TLS 1.2 is also still supported. Versions earlier than this are deprecated. Internet Protocol Security Tunneling. Transport Layer Security is applied at the application level. Internet Protocol Security, IPsec, operates at the network layer of the OSI model, Layer 3. This means that it can be implemented without having to configure specific application support and that it incurs less packet overhead. There are two core protocols in IPsec, which can be applied singly or together, depending on the policy. Authentication Header, AH, performs a cryptographic hash on the whole packet, including the IP header, plus a shared secret key, known only to the communicating hosts, and adds this value in its header as an integrity check value, ICV. The recipient performs the same function on the packet and key and should derive the same value to confirm that the packet has not been modified. The payload is not encrypted, so this protocol does not provide confidentiality. Encapsulating Security Payload, ESP. can be used to encrypt the packet rather than simply calculating an ICV. ESP attaches 3 fields to the packet: a header, a trailer, providing padding for the cryptographic function, and an integrity check value. Unlike AH, ESP excludes the IP header when calculating the ICV. IPsec can be used in 2 modes. Transport mode is used to secure communications between hosts on a private network. When ESP is applied in transport mode, the IP header for each packet is not encrypted, just the payload data. If AH is used in transport mode, it can provide integrity for the IP header. IPsec datagram using AH and ESP in transport mode. Tunnel mode is used for communications between VPN sites across an unsecure network. With ESP, the whole IP packet, header, and payload is encrypted and encapsulated as a datagram with a new IP header. AH has no use case in tunnel mode, as confidentiality is usually required. IPsec datagram using ESP in tunnel mode.
Description.
The sub-option, Tunnel Settings under the tab VPN, is selected from the left menu. The right pane shows Mode, Tunnel IPv4 and Description, Remote Office. A section titled Local Network shows type, LAN subnet and address, blank 32. Another section titled Remote Network shows type, network and address, 102.480.24. Another section titled Phase 2 Proposal, SA/Key Exchange, shows protocol, ESP. Configuring a site-to-site VPN using IPsec tunneling with ESP encryption in the OpenSense security appliance. Screenshot courtesy of OpenSense. Rate your confidence. Internet Key Exchange. Each host or router that uses IPsec must be assigned a policy. An IPsec policy sets the authentication mechanism and also the use of AH/ESP and transport or tunnel mode for a connection between 2 peers. IPsec's encryption and hashing functions depend on a shared secret. The secret must be communicated to both peers, and the peers must perform mutual authentication to confirm one another's identity. The Internet Key Exchange, IKE, protocol implements an authentication method, selects which cryptographic ciphers are mutually supported by both peers, and performs key exchange. The set of properties is referred to as a security association, SA. Description. The fields under the head Phase 1 Proposal, Authentication, are as follows: Authentication Method, Mutual RSA. My Identifier, My IP Address. Peer Identifier, Peer IP Address. My Certificate, Structurality Site-to-Site VPN. Remote Certificate Authority, Structurality Enterprise Root. The fields under the head Phase 1 Proposals, Algorithms, are as follows: Encryption Algorithm, 256-bit AES-GCM with 128-bit ICV. Hash Algorithm, SHA-256. DH Key Group, 14 2048 bits. Configuring IKE for certificate-based authentication in the OpenSense security appliance. Screenshot courtesy of OpenSense. IKE negotiations take place over 2 phases. Phase 1 establishes the identity of the 2 peers and performs key agreement using the Diffie-Hellman algorithm to create a secure channel. 2 methods of authenticating peers are commonly used. Digital certificates are issued to each peer by a mutually trusted certificate authority to identify one another. Pre-shared key group authentication is when the same passphrase is configured on both peers. Phase 2 uses the secure channel created in Phase 1 to establish which ciphers and key sizes will be used with AH and/or ESP in the IP SEC session. There are 2 versions of IKE. Version 1 was designed for site-to-site and host-to-host topologies and requires a supporting protocol to implement remote access VPNs. IKEV 2 has some additional features that have made the protocol popular for use as a standalone remote access client-to-site VPN solution. The main changes are the following. Supports EAP authentication methods, allowing, for example, user authentication against a Radius server. Provides a simple setup mode that reduces bandwidth without compromising security. Allows network address translation, NAT, traversal, and Mobike multi-homing. NAT traversal makes it easier to configure a tunnel allowed by a home router/firewall. Multi-homing means that a smartphone client with Wi-Fi and cellular interfaces can keep the IPsec connection alive when switching between them. Rate your confidence.
Continue.
Remote desktop. A remote access VPN joins the user's PC or smartphone to a remote private network via a secure tunnel over a public network. Remote access can also be a means of connecting to a specific computer over a network. This type of remote access involves connecting to a terminal server on a host using software that transfers shell data only. The connection could be a client and terminal server on the same local network or across remote networks. A graphical remote access tool sends screen and audio data from the remote host to the client and transfers mouse and keyboard input from the client to the remote host. Microsoft's Remote Desktop Protocol, RDP, can be used to access a physical machine on a one-to-one basis. Alternatively, a site can operate a remote desktop gateway that facilitates access to virtual desktops or individual apps running on the network servers. RDP connections are encrypted by default. There are several popular alternatives to remote desktops. Most support remote access to platforms other than Windows, macOS and iOS, Linux, Chrome OS, and Android, for instance. Examples include TeamViewer, teamviewer.com/n, and Virtual Network Computing, VNC, which is implemented by several different providers, notably realvnc.com/n. In the past, these remote desktop products required a dedicated client app. Remote desktop access can now just use a web browser client. The Canvas element introduced in HTML5 allows a browser to draw and update a desktop with relatively little lag. It can also handle audio. This is referred to as an HTML5 VPN or as a clientless remote desktop gateway, Guacamole, Apache.org. This solution uses a protocol called WebSocket, which enables bidirectional messages to be sent between the server and client without requiring the overhead of separate HTTP requests. Rate your confidence. Secure Shell. Secure Shell, SSH, is the principal means of obtaining secure remote access to a command line terminal. The main uses of SSH are for remote administration and secure file transfer, SFTP. Numerous commercial and open-source SSH products are available for all the major NAS platforms. The most widely used is OpenSSH, openssh.com. SSH servers are identified by a public/private key pair that is referred to as the host key. Host names can be mapped to host keys manually by each SSH client, or through various enterprise software products designed for SSH host key management.
Description.
The warning message reads, "Continue connecting to an unknown server and add its host key to a cache?" The text below reads, "The server's host key was not found in the cache." You have no guarantee that the server is the computer you think it is. The server's RSA-2 key fingerprint is SSH-RSA 2048 Candelas:8B:11A:52:52:52:D4:24:82:99:D8. If you trust this host, press yes. To connect without adding host key to the cache, press no. To abandon the connection, press cancel. 5 buttons, yes selected, no, cancel, copy key, and help are at the bottom. Confirming the SSH server's host key using the PuTTY SSH client, screenshot used with permission from PuTTY. The host key must be changed if any compromise of the host is suspected. If an attacker has obtained the private key of a server or appliance, they can masquerade as that server or appliance and perform a spoofing attack, usually with a view to obtaining other network credentials. The server's host key is used to set up a secure channel to use for the client to submit authentication credentials. SSH Client Authentication. SSH allows various methods for the client to authenticate to the server. Each of these methods can be enabled or disabled as required on the server, using the /etc//ssh/sshd_config file. Username, password, is when the client submits credentials that are verified by the SSH server either against a local user database or using a Radius server. Public key authentication is when each remote user's public key is added to a list of keys authorized for each local account on the SSH server. Kerberos is when the client submits the Kerberos credentials, a ticket-granting ticket, obtained when the user logs onto the workstation to the server using the generic Security Services Application Program Interface, XAPI. The SSH server contacts the ticket-granting service in a Windows environment. This will be a domain controller to validate the credentials. Managing valid client public keys is a critical security task. Many recent attacks on web servers have exploited poor key management. If a user's private key is compromised, delete the public key from the appliance and then regenerate the key pair on the user's remediated client device and copy the public key to the SSH server. Always delete public keys when the user's access permissions have been revoked. SSH commands. SSH commands are used to connect to hosts and set up authentication methods. To connect to an SSH server at 10.10.10 using an account named Bobby and password authentication run. SSH Bobby at 10.1.0.10. The following commands create a new key pair and copy it to an account on the remote server. SSH keygen, TRSA. SSH copy ID Bobby at 10.1.0.10. Add an SSH prompt. You can now use the standard Linux shell commands. Use exit to close the connection. You can use the scp command to copy a file from the remote server to the local host. scp Bobby at 10.1.0.10/log/audit. Log audit log. Reverse the arguments to copy a file from the local host to the remote server. To copy the contents of a directory and any subdirectories recursively, use the R option.
When it comes to secure remote administration protocols, Secure Shell is one of those de facto standards. Let's take a look here at kind of how Secure Shell works out of the box, and then once you've done a little bit of configuration. So I've got an Ubuntu system here, and I'm going to connect to a remote system. My remote system here is my green little parrot system with the IP address of 192.168.109. Okay, so that's the remote system that I'm going to connect to. I'm just copying and pasting here so that I can do it very easily, because you don't want to see how badly I type in front of a camera. So basically, I'm going to use the SSH command here, and I'm going to connect to that system. Now, the first thing that happens is you get this little message here. It's not an error message, but it's saying, are you sure that this is the host that you want to connect to? I've never connected to it before. Here's the fingerprint. Is this really the system you want to connect to? And it's doing this because you're relying on passwords right now. So I'm going to say yes. And then it's going to say, well, what password do you want? And I know the password to that remote parrot green system here. See if I can get it right here. Type it right. There it is. Notice where it says parrotsec. I'm into that system. Well, there are a couple issues here with what I just did. Now I'm back into my Ubuntu system, so let me clear the screen. The first problem is that I did use a password, okay? And even though Secure Shell encrypts by default, it's never a good idea to throw a password across the a network. Why do that? Set up a trust relationship first. So one way that you can do that is you generate a key pair. And so I'm going to SSH-keygen, there it is, and I'm going to generate a key pair. And it's going to ask me where I want to put it. I'll just leave it to the default here. I will not use a passphrase. And there is my key pair. So what I can do here is I can go in here to my pub key here. I've catted it there. And for the sake of being very obvious, and I don't want to use any automated tools that do exist, I've copied this here system here, this key here, and I'm going to go here to my parrot system here, and I'm going to edit the authorized keys file. I'm going to put in the public key of that remote Ubuntu system in here. Now let me go back to the remote Ubuntu system here. Now basically what I've done is set up a trust relationship. So the next time I go into SSH and go in, notice what just happened. I've logged directly into Parrot without providing a password. That's not because SSH stored the password or anything like that. That's because I set up a trust relationship with this remote Parrot system, and I was able to get right in because it says, well, I already trust you, so there's no need for a password. When you do remote protocols such as this, it's always good to use those trust relationships. Although they can be abused if a hacker gets in another way, those trust relationships are very good because it allows you to not use passwords across the internet.
Out-of-band management and jump servers. A remote access management channel refers to the specific use case of using a secure network and shell application to administer a network switch, router, firewall, or server. The Secure Administrative Workstations, SAWs, used as management clients must be tightly locked down, ideally installed with only the software required to access the administrative channel, minimal web browser, remote desktop client, or SSH virtual terminal, for instance. SAWs should be denied internet access or be restricted to a handful of approved vendor sites for patches, drivers, and support. The devices must also be subject to stringent access control and auditing so any misuse is detected at the earliest opportunity. Out-of-band management. Remote management methods are either in-band or out-of-band OOB. An in-band management link shares traffic with other communications on the production network. The connection method must use TLS, IPsec, RDP, or SSH encrypted sessions to ensure confidentiality and integrity. A serial console or modem port on a router is a physically out-of-band management method. A network appliance can also be managed using a browser-based interface or a virtual terminal over Ethernet and IP. This type of management link is made out of band either by connecting the port used for management access to a physically separate network infrastructure or connecting to a dedicated management VLAN. This can be costly to implement, but out-of-band management is more secure and means that access to the device is preserved when there are problems affecting the production network. Jump servers. One of the challenges of managing hosts exposed to the internet, such as in a screened subnet or cloud network, is providing administrative access to the servers and appliances located within it. On the one hand, a link is necessary. On the other, the administrative interface could be compromised and exploited as a pivot point into the rest of the network. Consequently, management of hosts permitted to access administrative interfaces on hosts in the secure zone must be tightly controlled. Configuring and auditing this type of control when there are many different servers operating in the zone is complex. One solution to this complexity is to add a single administration server, or jump server, to the secure zone. The jump server only runs the necessary administrative port and protocol, such as SSH or RDP. Administrators connect to the jump server and then use the jump server to connect to the admin interface on the application server. The application server's admin interface has a single entry in its ACL, the jump server, and denies connection attempts from any other hosts. Description. The steps are as follows. 1. A VPN can be used to access the jump server, which authorizes and forwards management traffic to the app server. 2. Management traffic from authorized hosts on the network can also be routed via the jump server. 3. Management traffic from unauthorized hosts is not permitted. 4. The app servers only accept management traffic connections from the jump server. 5. Ordinary application traffic uses a different network. Securing management traffic using a jump server. Images copyright 123rf.com. Rate your confidence.
Continue.
You should understand the use of segmentation to implement zone-based security topologies and be able to select appropriate control types and deployment locations to protect networks and hosts in given scenarios. Guidelines for implementing secure enterprise network architecture. Follow these guidelines when you implement designs for new or extended networks. Identify business workflows and the servers, clients, protocols, and data assets that support them. Design segmented network zones or blocks that support the security requirements, using VLANs, subnets, and firewall policies to implement the design. Deploy switching and routing appliances and protocols to support each block, accounting for port security or 802.1x network access control, NAC. Analyze the attack surface and select effective controls deployed to appropriate network locations. Deploy port security or 802.1x NAC to mitigate risks from rogue devices attached to physical network ports. Deploy routing firewalls to enforce access control and intrusion prevention at zone perimeters, utilizing Layer 4 or Layer 7 filtering as appropriate. Deploy transparent firewalls to protect hosts and segments without having to change the IP topology. Deploy sensors for intrusion detection behind firewalls or on a mirrored switch port to monitor traffic within a zone. Consider the use of proxy servers and GFW and WEF for advanced application and user-aware filtering. Consider the use of UTM to deploy additional security control capabilities alongside firewall/IPS functionality. Design load balance services to provision high availability and fault tolerance. Accommodate remote access client-to-site, site-to-site, and host-to-host secure communications requirements with TLS and IPsec VPN protocols. Implement secure communications for desktop/shell remote access with RDP and SSH. Consider the use of a jump server to consolidate the management of a group of servers in a protected zone. Rate your confidence